Hello, welcome. So this is me doing a practice lecture for Math 321. This might be a bit slow, I don't know, but we'll see. I am practicing giving the lecture for the University of Wollongong. Sorry, Math 204. I'm teaching 321 as my other class this semester at the University of Wollongong. Okay, so I'm practicing this for two reasons. The first is because I want to get the timing right for the class, and the second reason is because I want some kind of record of my lecturing for the students so that they have something to go and look at. I'm not convinced that recording the lectures works terribly well, so I'm going to try this out. Okay, so Math 204 is complex analysis. Let's say complex variables, I think is what the actual name is. And group theory. Okay, so there's a lot of connections between group theory and complex variables, but I'm not sure that that's reflected in the course notes. So we'll see as class goes on, because this is my first time teaching it. Anyway, I hope that this works reasonably well for you all. We'll see. Okay, Okay, so the first thing to do with complex variables is what is a complex variable? And there's lots of different ways to introduce complex variables, and one of my favorite ways to introduce complex variables is actually related to group theory. Okay, so complex variables can be represented as ordered pairs of real numbers. Now this is not how I'm actually going to introduce them in the class, but I'll show how this is kind of related to the other approach. So this is what we're going to do first, and then I'll show this bit second. I actually like this bit way first because I think motivating complex variables by appealing to quadratic formulas, which is how this bit is going to work. Solutions, motivating complex variables by solutions to quadratic equations, I think is a little arcane. Now the reason for that is because by the time you do a second year class at university, I'm not sure that people have seen solutions to quadratic equations that kind of make sense in the real world. So where is the connection to the real world? Now there is a very strong connection, but the point is that people might not have seen this. And whereas this is a bit more abstract. It has lots of rules. So basically you write down the rules. Yeah, hold on a second. Apologies about that. So you write down the rules, and then you basically explain exactly how the rules kind of follow our intuition in some sense when one of the variables, one of the elements in the ordered pairs, this one, according to the rules, behaves a little like, or rather a lot, like how we would expect the square root of -1 to behave. So I kind of like that because I think it makes it clearer that we're inventing something and representing it in some way, and then it behaves like some other thing, and then you can kind of do stuff. But this is perhaps a bit more. This is very abstract and makes, I think, a lot of sense when you've done group theory. But this is more concrete because people have seen quadratic equations before. But again, the connection to the real world might be missing a little bit. Okay, so complex variables. Let's say you want to know what solutions are to this quadratic equation, and the solutions there's two of them, and they come from the quadratic formula. Okay. So it's worthwhile knowing where this comes from. So I'm just going to we'll do something called completing the square. Okay. So let's say you have a formula, x plus, well, I'm going to use different variables, d squared, right? And this is always going to be equal to x squared plus 2d x plus dx. rewrite that out. X squared plus 2dx plus d squared. And you can compare this to that and ask, well, what are the differences? Well, so we can take the a out. Let's take the a out. Right? Is equal to 0. And this bit inside the brackets kind of looks like this. Kind of. But where d has to have a particular form. I mean, b and c might not, but yeah. But we're going to add in. So let's say we have this bit here. So this, if we consider about this, we want to try and convert it into that kind of form. So this term here needs to be 2d. So we have b a has to equal 2d, or d equals b over 2a. So now we can ask what the result of this is. So let's write down this a x plus b over 2a squared. Well, this is equal to a times x squared plus b a x plus b squared over 4a squared. And this is clearly different from that, right? But you can see what terms might be missing. We can add them in, take them off, so we change by 0. So let's write this out. A x squared plus b over ax plus, what's the right way to do this? The a is kind of annoying, I suppose, isn't it? Anyway, let's we're going to try and rewrite this in that form. So let's I suppose let's ignore the a, right? Let's put the a outside. X squared plus b over ax. We need to add in this term. So that's completing the square. So that's making it so that we can, this is a square, right? So we can undo this. But we've added this in. It's non-zero, so we need to make sure we take it out. There we go, we've taken it out. And we need to make sure we have our other remaining term. Right. This bit here is equal to that bit there, and this bit here is equal to 0, so this is equal to 0. Right, so then we have a x plus b over 2a squared minus, and I'm multiplying through by the a here, so 0 is equal to b squared over 4a plus c equals 0. So then we have a x, so we're going to take these bits over to the other side. Multiply through by, I guess divide by a. And let's make this one fraction. So the bit that's missing down here to make this denominator the same as this denominator is 4a. So b squared plus 4 minus 4ac divided by 4a squared. We take the square roots of both sides. X plus b over 2a equals 2. And remember, when you take a square root, it could be positive or negative. The square of 2 is 4. The square of minus 2 is also 4. Right. Yeah. Square root b squared minus 4ac divided by, and we can take the square of this directly. That's my 2a. X is equal to minus b plus or minus square root b squared minus 4ac divided by 2a. Okay, so just finding out somewhere to put this. I don't want to throw it away. Let's put it up there. Okay. Right, now you'll have all seen before that this equation has some different interpretations. Right? So if b squared minus 4ac is greater than 0, then we have two roots. Right? So we have two different roots corresponding to the plus or minus sign, and we know that our original equation just looks something like this: y equals ax squared plus bx plus c, and there's the two roots that differ by square root of b squared minus 4ac over 2a. Differ by two lots of that. In the middle somewhere is minus b over 2a. Okay, so when b squared minus 4ac equals 0, then we know that our equation must be something like this, with one root, and that root happens at minus b over 2a, because this bit is 0. So what happens when b squared minus 4ac is less than 0? Now, maybe you've been shown this at high school, I'm not sure, but a lot of people haven't, and the question ends up being, just avoid it, right? Because if you want real solutions, this has no solution. Not defined in the reals. Yeah, so here the parabola looks something like this. No roots, because you don't cross the x equals the y equals 0 axis. But we could pretend. So this is negative, right? So b squared minus 4ac is going to be equal to the negative of some number d, where d is greater than 0. So in this case we could write x equals minus b over, plus or minus, square root of minus d over 2a. And we could write this as minus b plus or minus square root of minus 1 times square root of d over 2a. And what we would need at this point is to know what on earth this means. We know what square root of d is, because d is positive, and we know what b and a are, but we don't know what square root of minus 1 is. Okay, so an example. In the notes, this is example 1.1. X squared plus a plus 1 equals 0. Right? So here a equals 1, b equals 1, and c equals 1. So b squared minus 4ac is equal to 1 minus, 4 times 1 times 1, which is equal to minus 3. So d is equal to 3. And x is equal to minus 1 plus or minus the square root of minus 1 over square root of 3 over 2. Right? Or another way to put this, minus 1/2 plus or minus square root of 3 times square root of minus 1, which is, I've forgotten a half. There you go, which is in the notes. So again, this thing is the thing that is preventing us in some sense. But we could always pretend that we know what that thing is. I mean, square root of, let's take a number, square root of 3. We know how it behaves. So square of square root of 3 is equal to 3. And the same is true for any positive number. Square root of d squared is equal to d. So this should imply that the square of minus 1, the square of the square root of minus 1 is equal to minus 1. Cute, huh? We made up a rule. Well, we had a rule, and then we said, well, what happens if maybe we just treat it like this? So this is basically one of the rules for dealing with complex numbers. Okay, so in mathematics, the letter I is typically used to denote the square root of minus 1, and we use that, I suppose, because writing square root of minus 1 is a bit cumbersome the whole time, and I is a bit more direct. I like it also because it tends to emphasize that the square root of minus 1 is a thing that we've made some rules up to associate with. Now, even though we've made some rules up to be able to describe how this thing behaves, I ends up being phenomenally important. I mean, you might see this in electronics, and the classic example is you need to have I involved in order to do to make equations involving electrodynamics work. But I ends up everywhere. I mean, and everywhere. As you will see later on in the class, this number is actually kind of related to rotations. And so whenever you have rotations or things that twist things, I often turns up, or at least something that behaves a bit like or can be interpreted like the square root of minus 1. So in other words, something that when you square it, you get minus 1. It turns up a lot, and even in general relativity. So this is my background, is in general relativity. And in general relativity, people often talk about taking complex time. So in this case, what they mean is, instead of measuring time using the real numbers, they measure time using I times the real numbers, right? So the square root of minus 1 times the real numbers. And the reason for this is because of the way in which time is represented mathematically. There are negatives associated here, which makes some kinds of calculations very difficult. But if you put a complex bit in, then the negatives become positives, which for various reasons that are not that are difficult to describe at this point in your mathematical education, this becomes very useful. So there's a whole thing called Euclidean gravity, which has been very successful, and this kind of the process of going from the real numbers into I times the real numbers is often called a Wick rotation. Rotations and complex numbers are related to each other. Anyway, point is, even though we've just made up a symbol for the square root of minus 1, and we've said that it's going to obey this rule, that I squared is equal to minus 1, it's a phenomenally useful device in mathematics, and without this, a lot of things in mathematics would be extremely difficult to do. And as you go on in the class, you're going to see some really, really cool theorems to do with complex analysis. And complex analysis comes up all over the place. For example, the Riemann hypothesis, which again I don't really want to describe because it's going to go quite a long out of the way, and there's some material you need to see before you really see this. But anyway, the Riemann hypothesis is that a certain function, which I always write incorrectly, I need to check. I need to check this. Hold on a second. Alright, sorry about that. Okay, I have checked this and I have details now. That was page 3. Anyway. So, the Riemann zeta function, which is a very important function in mathematics, Riemann zeta function. Zeta of S is the sum from n equals 1 to infinity of 1 over n to the s, right? So this is equal to 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s, and so on to infinity. Okay, so this is a function, and it is phenomenally important. It doesn't have any real zeros. These are all positive numbers, and they're all summed up, so there's no real zeros. So does not equal 0, on the real numbers. But the complex zeros are very important and related to prime numbers. It's one of the biggest outstanding problems in mathematics. A lot of people are very keen on studying this, so go read the Wikipedia page. But I don't give you any promises about understanding it. You'll have to work through some of the notation and definitions there. Yeah. But anyway, hugely important, all related to complex numbers. So complex numbers are very, very important. Okay, now I've written down I equals to square root of minus 1. And it's important to note that some people use j equals square root of minus 1. In particular, engineers do, because I is electric current. So just remember, sometimes you're going to see square root of minus 1 written as an I, but for me and for this class, it's always going to be square root of minus 1. Okay, so complex number, right? Definition. This is 1.1.3 in the notes. Complex number. So we take x and y, an element of the real numbers, then x plus I, y is a complex number. Don't let my notation, I've been writing it with a script, but also you can write it like this, so don't worry. Yeah. Is a complex number. Okay, so the set of all complex numbers, right? 5 is written C, which is equal to x plus I, y, for x and y, an element of the real numbers. Okay, so that x, y, yeah, and in the notes we have c and d, the elements of the real numbers. Then x plus I, y is equal to c plus I, d, if and only if x is equal to c and y is equal to d. Now, do you remember that example 1.1, which I guess when I actually give the lecture, I really hope I've left on the board for you. So do you remember I wrote this as x equals minus 1/2 plus or minus square root of 3 over 2 square root minus 1? Right. So now we can write those, and this is for the equation. Right. So if we interpret this thing as an element of the complex numbers, then we can write that the roots of x squared plus x plus 1 are the complex numbers minus 1/2 minus square root of 3 over 2 I, and minus 1/2 plus square root of 3 over 2 Okay, so let me prove that for you, because I think this is important to see. There's a bit of calculation involved. Minus 1 over 2 plus square root 3 over 2i squared plus minus 1/2 plus I plus 1. Okay, so now you need to ask how. There's some calculations in here, right? So when you square a complex number, what happens? Well, you just times everything together like you're dealing with real numbers. So this ends up being minus 1/2 squared plus 2 lots of minus 1/2 3 over 2 times I, yep, plus square root 3 over 2i squared minus 1/2 plus square root 3 over 2i plus 1. This is equal to, well, that's a quarter. And this 2 cancels that 2, so we get a minus. Let's get minus square root 3 over 2i. And plus, we get 3 over 4. And I squared is minus 1. Minus 1/2 plus square root 3 over 2i plus 1. So the two complex bits cancel out, and then we're left with this thing here. So 1/4 minus 3/4 is minus 1/2. Minus 1/2 gives us 1, plus 1 gives us 0. So it does work. And don't worry, we'll go through the details of exactly what that calculation is as we go through. So anyway, it does work. Try it out for the other root. See what happens. Okay, so an important number thing. These two roots are represented as minus 1/2 minus I over 2 and minus 1/2 plus I. And these two things are related. They're related by something called complex conjugation. Okay. So 1.1.5 definition. So we take Z or Z. Sorry. So you can write Z's this way. You can also write Z's like this, and I have a tendency to write them this way. So for that, I apologize. I'll try quite hard to write them this way, but I might write them that way, in which case I'm sorry. But just so you know. So Z is typically used to denote an element of the complex numbers. So that must be x plus iy, an element of the complex numbers. So the complex conjugate of Z you can just call it the conjugate. Yeah. So if we write that Z is equal to x plus I, if we write that Z is equal to x plus iy, then the complex conjugate x minus iy is written Z with a bar over the top. So that denotes conjugation. Okay. Conjugation is extremely important and is going to come up much later on in the class again and again and again and again and again. It's very important. So in the solutions to the quadratic equation, note that we had these two things being conjugates of each other. I've changed the sign in front of the I from a plus to a minus. Right, so if I have x plus I y, I can also just put a bar straight over the top to denote that that's the conjugate. Right, and so this is equal to x plus x minus iy. And just to be clear, x minus iy conjugate. Or you can write this as, like, let's just be super obvious about this. So x plus I minus y. This is a real number, right? So it kind of looks like this. There's a plus sign, you put the minus sign, so this is equal to x minus I minus y, x plus I y. The point being that x plus I y, complex conjugate of the complex conjugate, is just equal to the original number. And in the notes you'll see this written as, okay, lots of lines all over the place and a little hard to see what's going on, but yeah. Okay. Now there's a cute result which follows from all of this, and this is in the notes, lemma 1.17. Okay. If the equation ax squared plus bx plus c equals 0, with a, b, c element of the reals, and a is not equal to 0, if the equation blah 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 with a, b, c in the reals and with a not equal to 0 has a root which is not a real number, so that must be a complex number, then the equation's roots are two different complex numbers that are conjugates of each other. Okay, and by that I mean that, for example, if u is a complex number, so that au squared plus bu plus c equals 0, then a, the complex conjugate of u squared plus b times the complex conjugate of b plus c equals 0. Right. So I'm not going to prove this. Proof for u. You have seen everything so far you need to prove this. Use the quadratic formula, and you can just basically back substitute in, but it's up to you, right? This is, I'm not going to do it. And it's page 7. Okay, so that was a basic introduction to the complex numbers. So now we're going to go on to section 1.2, which is about geometry and the polar form of complex equations. So this is the first time we're going to see this pairing. A plus IB, yeah. So we can think of this as a point AB inside the real plane. Right. But we can write this also as A plus IB, where this is I times the real numbers, and this is an axis which gives the real numbers. Right. So this bit corresponds to this thing over here, and this bit corresponds to this thing over here. Okay. So some examples. I equals 0 plus I times 1. So we have 0 on this axis, we have 1 here. So that's the point 0, 1, which can be written as I. 1 equals 1 plus I times 0. So there's a 0 pure complex bit and 1 real bit. So that's that point there. 1, 0, right, which we can also write as the number 1. Okay, so let's do 2 plus I. 2 plus I times 1, which is what, roughly equivalent to the pair 2, 1. So I'm going to come along here to this 1, there's 2, and that goes there, right? Maybe I should put a minus sign. Let's put a minus sign, minus sign, minus sign. Okay, so we're going to go negative on the negative bit and up 1, so that's there. This is the point minus 2, 1, which can also be written as minus 2 plus I. Just a different way to represent the same thing. But again, like everything you've seen so far, very, very useful. This thing here is called the complex plane, or also sometimes called the Argand plane, after a fellow whose name was Argand. Argand plane, not planar. So the notes say French mathematician. Anyway, it's actually very important. You'll see that, see how 1, if I multiply, well, no, you'll see it soon. Okay, so this is very, very important. Okay, so given a real number, we can ask, what is its real bit? The real bit of a complex number is just is x, and we can ask what the imaginary bit is. So these bits here, pure complex, pure imaginary, these bits here are called real. Definition. And that was probably earlier in the notes, and I have missed it when reading through. But anyway, if you're clever people, you can figure it out. Okay, so this is the real part, and this is the imaginary part. Right, now some of you, we're up to 8, some of you will have seen polar coordinates before. Polar coordinates are a thing which are you can use in the plane. So when you're doing multivariate calculus, for example, but they're very useful in complex analysis too. So we have some point x, y, x, y. So polar coordinates. Sorry, just taking things. Oh, yeah, polar coordinates. I forgot to mention something which is probably going to come up at some point, and so I'll come back to this. Do you remember x plus iy corresponds to a point xy? So here's my xy. Right, so the complex conjugate of x plus iy is equal to x minus iy, which corresponds to the point x minus y, right? Because this thing is equal to x plus I minus y. That's down here. And this is a generic feature. If I take a point and I take its complex conjugate, it ends up being flipped on one side. So if I have a point over here, which might be, let's say 3 plus 1/2 I, its complex conjugate is reflected in the real axis. You'll see this again and again, so don't worry about this. But the point is that complex conjugation is reflection in the real axis. I think this is in the notes to emphasize the point that the complex plane provides a geometric viewpoint on the complex numbers, which up until now are just pairs of real numbers, right, with I involved. But complex conjugation actually does something geometric and flips things around. And there's lots and lots and lots of circumstances in which operations with complex numbers can be interpreted geometrically, and that geometric interpretation helps us understand what's going on. So there's lots of examples of that, and they'll come up during the class as the class goes on. So I'm just getting some paper. There you go. A nice boring YouTube video of sounds of someone getting paper. Okay, great. Where was I? Right, getting a little lost. I've got paper out now. You know, I'm sure this won't be the worst YouTube video around, but definitely not the best. My production values are pretty low, so, you know, basically because I can't be bothered. That's not true, but, you know, I only have a small amount of time to do all this stuff. Okay, sorry, let's move on. Section 1.2, polar coordinates. So we talked about representation on the complex plane. We talked about reflections. Complex conjugate is a reflection, which is important. Now we're going to talk about polar coordinates. Okay, so this works for the plane with real numbers, of course, as well. So this is based upon the representation of a complex number as a pair. Okay, so there's my pair. xy, which is going to be x plus iy. Okay, so polar coordinates. Now, the point xy can be measured using x on our real axis, and minus I on our imaginary axis. We can also measure it a different way. Let's think of a line through the point to the origin, and that line will have a length, which I'm going to call r for the moment. That is a world's most terrible R. And I'll also have an angle from the real line. So x and y can also be represented as r and theta. Now, there's going to be a closer relationship between these two things too, and I'll talk about that in a moment. The point is, for every point on the plane, there's going to be some angle that goes to it and some length and distance from the origin. Because the origin, the point 0, 0, is going to be equivalent to r equals 0 and theta equals something, right? Because you can't really define the angle. But, so apart from an oddity there, which will come up, I'm sure, again in a little bit in the future, every point can be represented in this way. Okay, now there's different conventions for the angle theta, and you may have seen some of these. So in radians, when you go around here, write this down. So this angle here in radians, right, this is 90 degrees, and in radians this is pi over 2. All the way over there, 180 degrees, it's pi in radians. Right, 3 pi over 2 pi. So let's consider a point over here. So I'll write it as x, y, so y is going to be negative. We can consider this thing here. So this is there, the line that we're talking about. Okay, so I can measure the angle from the real line this way around, which will be some value bigger than 3 pi over 2 and smaller than 2 pi. So in this particular case, measuring this way, we could say that theta is always going to be an element of 0 for points that lie on the line, up to 2 pi but not including it. And the reason we don't include it is because we don't want to double count, because if we put 2 pi in, the angle, angle 0, angle 360, same thing, so don't want to double count. The other way of doing this is to consider this point, 10, 11, and to consider going backwards. So we'll always measure counterclockwise for positive and anti-clockwise for negative. So this is a negative angle, and of course going backwards this would be minus pi over 2. And I want to say that I mean the negative angle this way would be minus pi over 2, and the negative angle all the way over here would be minus pi. So in this case, if you want to measure like this, theta would be between minus pi and pi. So we include pi, don't include minus pi, and the reason for that is that from here to here is pi. So an element that had angle pi is going to be on the negative real axis, and we don't want to double count, because minus pi would be the same thing, right? You turn 180 degrees to your left or 180 degrees to your right, same thing, right? That's what this is expressing, right? And this is saying right, if I'm facing towards real positive infinity, so that means that I'm looking that way, right? Right, left. Okay, so there's different conventions. So this means that depending upon how you want to write things down, different points will have different different values for the angle, positive, negative, and so on and so forth. In fact, you could always add 360 degrees to everything, because if you turn 180 degrees, is basically the same as 180 degrees plus a full extra turn. So what's that? That's 540. Right. Anyway, point is, the angle is not necessarily unique. It matters how you measure it. And in this class, we're going to be principally measuring like this. Just something to watch out for as you go along, and to be aware of. Any of these conventions is perfectly fine. They're all basically the same, and when we want kind of to specify a particular range, we will. So don't worry about that. So anything is okay. Now, you can even have negative radiuses that R is meant to stand for radius. So you could have a negative radius if you really wanted to. Okay, so I don't, we're not going to. We want the length of the line to always be positive, but in principle you could have a negative one. So let's go. So here's our point X, Y. Okay, so this line is going to have some length, which I'll write as R, hopefully a bit better. The radius, because you can think about this on a big circle, which will be made more precise in a moment. And the angle here is going to be this one here, theta, which, if we consider this to be 45 degrees, let's say an example would be theta equals minus 3 pi over 4. Right, so, and the radius is, some value r. But I could write this as another angle, phi here. So in this case, phi would be equal to pi. And you can see, because it's 180 degrees, right? So 180 degrees is pi, and if you add pi to that, you get this. So theta plus pi equals phi. So, and the radius of this thing, which but this, remember I talked about array, so the length of the line is important. So what we would say is, ordinarily if we're measuring in theta phi, we would want to travel in this direction, up towards the positive numbers, but the actual point we want is negative. So in this case, the radius would be a negative, whatever that r is, and we want to avoid negative numbers. So radius, always positive. And if you end up in the situation where you have a negative radius, then it can be fixed, right, in a way that I've indicated here. So if you have an angle phi and minus r, you can r and phi, you can rewrite as, so minus r because we're traveling backwards. You can rewrite it as positive r phi minus pi. It's mentioned in the notes. If you want a little more detail about this, it's mentioned in the notes above example 1.2.2. Okay, so some examples. All right, we are going to start with the number z equal to 1 plus I, right? So that corresponds to 1.1. And we know what the length of this is because hopefully you've seen this before. Right angle triangle, right? So the length of that line, square root 2. And the angle here is pi over 4. Right, so the polar coordinates of 1, 1, r equals square root 2, and pi over 2, theta equals pi over 2, which we write as square root 2 pi over 2. Okay, now there's a little important piece of information. When I wrote this down, I didn't tell you. We knew implicitly this 1.1 was Cartesian because of where it had come from. We know implicitly that this thing here is polar. But so when you write down pairs of coordinates, it's sometimes necessary to explain which coordinate system you're using. Cartesian coordinates, polar coordinates. Cartesian coordinates normally mean the normal x, y coordinates. Okay, so you can use the normal kind of trig identities to write down equations for these things. That's a angle. That's a side of a triangle. It has length y. This has length x. So the normal equation is that r equals the square root x squared plus y squared. And you want to know this angle here. What we know is from trig identities, because this is a right angle triangle, that x equals r cos theta and y equals r sine theta. SOHCAHTOA was how I always remembered this. Sine of opposite over the hypotenuse. So the sine of the angle is the opposite, which is y, over the hypotenuse, which is r. Cosine, cos of the angle equals the adjacent over the hypotenuse. Right, so we want to write this down in some nice clean way. Okay, so polar coordinates to Cartesian turns out to be the easy one. And do you remember how I've been kind of implying that there's lots of different ways to write down coordinates in polar form, even if you assume that the radius is always positive? Well, that's going to come up in just a moment. So it's easy to write polar to Cartesian. We have this down, so we have r theta goes to r cos theta sine theta, or to put it another way, x equals r cos theta, y equals r sine theta. Okay, now Cartesian to polar is harder, and this is precisely because there's lots of different ways to write down Cartesian coordinates multiple ways in polar form. And you can always add 360 degrees. You could take negative angles. You could take positive angles. It's not great. Now we know that the radius is always so we have x, y, and that is going to go to something, the radius and the angle. We know that the radius is always going to be x squared plus y squared, so that's great. And what we can say about the angle theta is that theta satisfies tan of theta equals x over y. And we can't take the inverse here. The inverse is not defined because there are multiple angles that can satisfy y over x. So in particular, y over x is also equal to minus y over minus x, right? So if we have theta, so that tan of theta equals y over x, then this happens to also be equal to minus y over minus x. And we know that we have two different angles and that they differ by pi. And it turns out that solutions of tan theta will differ by pi. So you can't take an immediate inverse of this equation. So let me say a little more about that, because basically theta is not uniquely determined. The missing information. So what should I say? This does not uniquely determine theta. Solutions differ by pi. The extra information that's needed is which quadrant of the plane the point lies in. So when I say quadrant, I mean these four squares, right? This is one quadrant, this is another quadrant, here's one more quadrant, and this blank bit is the fourth quadrant. There's four quadrants that divide up the plane, and the information that you need to accurately determine the solution for the tan theta equals y over x is which quadrant we lie in. So this is worth emphasizing even a little more. I apologize if you've seen this before, but it really is worth saying again and again. So here's a graph of tan theta. Pi over 2. Pi. 3 pi over 2. Minus pi over 2. Minus pi. Okay, so what does this look like? This is theta here. This is tan theta, which is also our ratio, x over y. So it asymptotes. Yep. And it repeats that every pi. Okay, so let's say we have some ratio. So this is y over x. We can ask what possible values of theta does it equal to? And there's an infinite number, right? It could be equal to this value, or this value, or this value. How do you know where to put it? Well, if you do a little bit of thought about this, and I suggest that you do this yourself, the values of theta in this segment here correspond to quadrant 1. 1, 2, 3, 4. And values in this quadrant, values of theta that lie in here, this intersection here, value to angles of theta in quadrant 3. This is quadrant 2, and this bit over here that's missing is quadrant 4. And you can work backwards, right? So this is quadrant 4 as well. This is quadrant 3. This is quadrant 2. So when converting from Cartesian coordinates into polar coordinates, you need to know which quadrant you're in. And that will help you to determine x and y, which will help you work out what the ratio is. And this all boils down to the fact that y minus x is equal to minus y over minus x, right? So if you have x and y over here, minus x and minus y lies in 3, so you have quadrant 1, quadrant 3. And they differ by pi. Okay, now this is a problem which comes up all the time, right? Whenever you're doing this kind of thing. So in some areas of science, particularly computer science and engineering, but in other areas too, they have they talk about a function called the two argument arctan, or tan inverse, two argument arctangent. So this is a function which is in a lot of programming languages and programming libraries. It's usually described as a tan 2. So this is basically tan inverse, which knows about quadrants. Okay. So this thing here, right, so tan theta equals y over x. So tan inverse takes y over x, which equals theta. This is a ratio, right? And the ratio is the thing which loses the information about quadrants. A tan 2 takes its two arguments, which is usually denoted x and y, and it returns theta in the correct quadrant. And it can do that because it does not use a ratio. The actual formula is kind of complicated and probably not very interesting or terribly important by itself, mainly because it's used in programming languages. But anyway, that's something to be aware of, I think. Right. Okay, so now we're going to stop using pairs. We're going to start using i's to represent these things. So z equal to x plus iy is an element of the complex numbers, right? Think a pair, which is what we've been doing for the moment. Now, we want to know about the polar equations. So this is Cartesian form. And in polar form, we're going to have these two things. You know, modulo all the discussion about awkwardness of theta, there's always going to be some value that makes it work. So, yeah. And we know that we can go from polar to Cartesian. So polar to Cartesian. We know that well, we know that x is equal to r cos theta and y is equal to r sine theta. So z, which is equal to x plus iy, is also equal to r cos theta plus I sine theta with an r that I've got, yep, or r cos theta plus I sine theta. Yeah. Okay, I think I missed something in the notes, which is probably worth covering, which is some examples. Ugh. Yeah, I missed some examples. Let's do some examples. Besides, I've forgotten what page I'm on, right? 17. And if you guys are still listening to me, anybody still listening to me, you are a machine. Well done. I'm sure this has not been easy. Okay, so in the notes, this is problem 1.2.4. Okay, so let's suppose we have a point with polar coordinates, 2 pi over 3. What is r? What are this point's? What is this point's Cartesian coordinates? Okay, r equals 2, theta equals pi over 3, which, you know, we know that pi over 2 is here, pi over 3 is less, so it's going to be something like this. Right? I guess I should do it like this. Pi over 3, 2. Now, x is equal to 2 times cos pi over 3. Cos of pi over 3 is a half for some magic reason that I always forget, but you know, it's written in the notes. Notes can't be wrong, right? Sine pi over 3 equals 2, and sine pi over 3 is square root 3 over 2, which equals square root 3. So the Cartesian coordinates are 1 square root 3. And again, note that there's nothing, you know, without the word polar there, you wouldn't know whether this is polar or Cartesian. I've just told you. Again, you wouldn't know whether this is polar or Cartesian. I've just told you. There's context here that you need to know. So what does this look like on the plane? There you go. So this is 1 square root 3. And the angle here is pi over 3. And the length here is 2. Okay. Problem 1.2.5. I'm going to be a little quicker here, but so in Cartesian coordinates, I've done this one already. Cartesian coordinates, the point 1, 1, so x equals 1, y equals 1, right? R equals x squared plus y squared, which equals square root 2. And what we know is that tan theta has to equal, let's just put a minus 1 square root 2, because y squared is the same. This is minus 1 over 1, which equals minus 1, which is equal to minus pi over 4, and in fact plus any combination of pi for k and the integers, right? You can add as many full rotations either to your left or your right as you like, and this will be the same thing. Right, now remember we're aiming for theta to be in minus pi, positive pi, in which case the polar coordinates are square root 2 minus pi over 4. But unless we explicitly ask for this, any of these values would have been fine, right? Any of them would have been fine. I should repeat myself like Trump, shouldn't I? Any of them. Russia. Any of them would have been. I don't know. I can't do accents. So if you wanted theta to be in 0 to 2 pi, then minus pi over 4 wouldn't be right. But if we take k to equal 1, minus pi over 4 plus 2 pi, which is equal to 3 pi over 4, which is in the right bounds. So in this case, the polar coordinates would be square root 2 over 3 pi over 4. Okay, there's lots and lots and lots of different forms for the polar coordinates. Right, and it's again, you can always add multiples of 2 pi in. Because 2 pi is one full rotation. One full rotation. Anyway. Okay, good. Well, that's 17. Those are the examples. Apologies. Page 18. Right, now we're going to go on to right, 1.2.3 section. Yeah. Anyway, so what did I write down? We had, here it is, 19. Yeah, sorry about that. Okay, so this is Cartesian form. This is polar form. Just like for ordered pairs, you need to say which is which, because it matters. Okay, so this form tends to highlight algebraic things, and this form tends to highlight geometric things, but that's not always the case, and useful for different reasons. Often in mathematics, it's rewriting some equation in a different way can help to provide insights because you understand it in a different way, and that's just like this here. This actually turns out to be very, very important, and it'll come up later as a key way of doing things. And if we didn't have this way of swapping backwards and forwards, writing the same equations that we could write with polar form that look simple would be very complicated on Cartesian form, and I don't really want to do it, and you wouldn't want to look at it. So it's actually maybe more important than it looks. It's so important that we have definition 1.2.8. Yeah, I don't like this section thing. I would like, this is a subsection, right? Subsection. And subsections numbers aren't indicated in here, which I don't like. If you're going to put in subsections, put the numbers in, and then it's easier to track them in the paper, in the notes. Okay, well, so at the moment we've got x and y for Cartesian form, and we have r theta for polar form. So what if I take a different number, which we've previously written as CD? Right, I can write this down, but let's maybe use S and psi or something. Anyway, all the symbols get confusing. and they kind of jumble things up and they can make it difficult to track. So it's important to have some definitions for these things. So we need definitions that indicate which complex number they came from. And you will see why this is important soon enough. So, if z is equal to x plus iy, the modulus of z modulus is written like this, and the modulus of z is equal to square root x squared plus y squared. So this is the radius, right? That r, the length of the line, line segment. Anyway, right. And the argument of z, which is written arg z, is any theta so that, oh, it's a cliffhanger. You have to wait till I turn the page. Oh, turning the page, 18, no! So it's any theta so that x plus iy is equal to the modulus times cos theta plus I sine theta, right? And you know that you can always add multiples of 2 pi to this thing. So this can be lots of different values. Any theta for this works. Right? Now we define principal value, or principal argument. Right. Now this is written with a capital A. Is the value of theta so that theta is a value of minus pi and pi inclusive. So arg z does not take multiple values. Well, arg z with a capital A does not take multiple values, but the argument with a lower A does. So, little diagram in the notes. 0. Right, the argument, the principal value of z is greater than or equal to 0. And the principal value of z is less than or equal to 0. Minus pi. In the book, they left the minus sign out from the diagram, so just that's a mistake. And in particular, right, minus pi is not included. So, in particular, the argument of z can never equal minus pi. Right, this is incorrect because we're excluding minus pi. Okay, so now that we've got some nice notation which makes the radius and the angle indicate, dependency on z, the modulus, and the argument, that means we can now write down equations using these things, which is nice. Okay, so this is lemma 1.2.9. Okay, so before I state this thing, well, no, I'll just write it down. Okay. Given R, an element of the real numbers, the numbers Z inside the complex numbers, so that modulus of Z is equal to R precisely those complex numbers which lie on a circle of radius R, centered at the origin in the Argand plane. Right. In particular, the modulus of the complex numbers that are equal to 0 if and only if the complex number itself equals 0. Okay, so proof. Z equals x plus iy implies that the modulus is equal to the square root of x squared plus y squared. Thus, if R is equal to this, the modulus, then x squared plus y squared equals R squared. So that, no, since the equation x squared plus y squared equals R squared gives a circle with the required properties, we have the result. Or another way to say it is, if you're a point lying on a circle of radius r, you have to satisfy this equation, which means when you work your way back, you have to be some x and y, some complex number, so that this equation is true. It's basically that. Okay. So this symbol here, sometimes called a tombstone. I've also seen it referred to as a halmos, after the mathematician who kind of pioneered its use in mathematics, called halmos. Anyway, it means end of proof. Okay. So now we have an example. Problem 1.2.10. Z equals 1 plus I. Find Z, arg Z, and the polar form. Right. Well, right. There's lots of different solutions to this. One of them is pi over 4, and that being inside the irrelevant range, we know that that's the principal value. So the polar form is, which you've seen all the time. Okay, so now we're going to do complex conjugation in polar form. z equals r cos theta plus I r sine theta. Works exactly the same way, right? The complex conjugate is equal to r cos theta minus I r sine theta. But we can also think about it another way, because we remember we had reflection in the plane. So if z is up here, then z bar is over here. So this is theta, this is minus theta. So z bar also happens to be equal to r cos minus theta plus I r sine minus theta. Right. Now, cos of minus theta is equal to cos of theta, and sine of minus theta is equal to minus sine of theta. So r cos minus theta plus I r sine minus theta is equal to r cos of theta minus I r sine of theta, as is required for the two different forms of the complex conjugate to be valid. Right, and this is related to even/odd functions. Okay, so we can write this all up in a nice little lemma, which may or may not be illuminating, but sometimes it's nice to collect facts in one of these things. 1.2.11. So z, an element of the complex numbers, implies the real part of the complex conjugate of z is equal to the real part of z. The imaginary part of the complex conjugate of z is equal to the negative of the imaginary part of z. We know that the modulus of the complex conjugate of z is equal to the modulus of z, and we know that the principal value of the complex conjugate of z is equal to minus the principal value of z itself. And we've already kind of proven this as we've gone through, but I'll do it again. Z equals x plus iy. Z bar equals x minus iy. So the real part of z bar is equal to x, which is equal to the real part of z. The imaginary part of z bar is equal to, this is equal to plus I minus y, which is equal to minus of the imaginary part of z. And the complex conjugate of z, the modulus of the complex conjugate of z is the square root of x squared plus y minus y squared, which is equal to x squared plus y squared, which is equal to the modulus of z. And we showed just before that if z is equal to r cos theta plus I r sine theta, then z bar is equal to r cos theta minus I r sine theta, which also happens to be equal to r cos of negative theta plus I r sine minus theta. The argument of z bar, well, the argument of this is, well, if we say minus theta, we write out z, if we write out z so that theta is equal to the argument of z, then this is equal to minus argument of z. So there's a little bit more work that I'm not talking about that much in there, but yeah. And that takes us all the way through to the end of section 1.2 of the notes. which hopefully should be the end of the first 2-hour lecture. There's probably a little bit left over, but yeah. Okay, so that was good for me, and I hope somebody who watches this finds that useful. Pretty slow and leisurely. Yeah, enjoy.